Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we continue our discussion on Lagrange equation of motion, starting with our concept of Lagrangian. Okay, so since what we have is V is V of Q, and partial V partial Q J dot is 0, and we see that V is the potential. We associate capital V with the potential of the system, right? Now, the potential typically will be a function of the generalized coordinate Q, but it won't be a function of Q dot. Remember, in the language of Lagrange formulation, in the language of calculus of variations, we are assuming Q dot and Q are independent variables. So now it turns out that dV dQj are 0 because V is explicitly a function of Q, not Q dot. So now in that case, we have that we can rewrite our equations of we can revisit our Lagrange equation of motion, that is d dt of partial t partial qj dot minus partial t partial qj and this is also equal to d dt of partial v partial qj dot minus partial v partial qj, right? What has happened is, since we know that this quantity is 0, I have added a quantity which is 0. Now to do that, what now we can do is we can now combine this right hand side and shift it on the left hand side. So now my new equation is d dt of partial qj dot of t minus v, right, minus partial qj of t minus v is equal to 0. Now I define my quantity which is the Lagrangian, which is t minus v, and now what I have is the Lagrange equation of motion, or which is the same Lagrange equation of motion, which is now written in the terms of Lagrangian, which is partial qj dot of L minus partial qj of L, and this is equal to 0. So that is my Lagrange, same Lagrange equation of motion in terms of Lagrangian. So that is my new quantity Lagrangian that we have introduced. So for example, let me just show you with an example. So for our driven pendulum case, we see that L of theta comma theta dot comma t. Now I am introducing Lagrangian with the notation capital L. So L of theta comma theta dot comma t is half m comma m of a theta dot square plus, Lagrangian will be kinetic energy minus potential energy. So the kinetic energy is a theta dot square plus z dot square minus a theta dot z dot sine theta plus mg z plus a cos theta. And now this is the last term is the negative of the potential, so we have put a minus sign which has produced a plus sign. So that is my Lagrangian. So now that is my concept of Lagrangian. It is simple. It is T minus V, kinetic energy minus potential energy. So now let us also introduce another variable, the so-called velocity potential. Velocity potential. Okay. So velocity potential. So what does again? So the idea is we have introduced the Lagrangian assuming that the potential energy of the system exists. That is certainly not the case for non-conservative system. And for that system, the non-conservative system, we introduce another form of potential known as the velocity potential. Okay. So for certain non-conservative system, non-conservative systems, we have V does not exist. V does not exists. Okay, but their equations of motion can be written in the form of Lagrangian. Can be written in Lagrangian. Okay. So then suppose, so how is it possible? All I have to worry about is how to write down the right hand side of the Lagrange equation of motion, which is how to write down the generalized forces. We introduce a velocity potential so that they can be represented, they can represent the generalized forces. So what I just said is the following. Suppose the generalized forces can be written, the generalized forces can be written as Qj given by ddt of partial u partial Qj dot minus partial u partial Qj. Right? So I am forcibly introducing a new quantity capital U, which is the velocity potential, and this is equal to this form is equal to the generalized forces Qj. So these are my generalized forces Qj, this quantity here. Right? Now this is for some u which is a function of q comma q dot comma t. Right? So now again this time my Lagrangian this time will be L of q comma q dot comma t will be t minus u. So I have forcibly introduced the so-called velocity potential, whose definition is given by this equation that I have written here, circled equation. And now instead of the potential energy V, my Lagrangian is t minus u. So that is as general as you can get. So this is my velocity potential or velocity dependent. Well, let me be very careful. Let me call this as velocity dependent potential, not velocity potential. Why? Because the concept of velocity potential appears in magnetic systems, magnetohydrodynamics, which we will see through some examples later on. So let us not confuse the terminology here. Okay, so then, so now I have, as I just mentioned about a magnetohydrodynamic system, let us look at an example of that system. So the system that we have is this example, which tells us that a particle P of mass m and charge E, right, can move freely in the static electric field. The static electric field E is equal to E of R, right? And the static, let me write this statement and I'll explain. The static magnetic field B, which is B of R comma T. So now the electromagnetic field, the electromagnetic field, the electromagnetic field exerts a force according to the Lorentz formula, right? So what is the Lorentz formula? Well, people who are doing this course need not remember what is Lorentz formula. I am going to state it. The net external force due to the electric field E times capital E plus E times V cross capital B, where V is the velocity of the particle and B is of course the magnetic field. So V is the velocity of the particle, P. And now we have to show that this force can be represented with a velocity dependent potential which is u of r comma r dot. So we have to find this u, okay, and find the Lagrangian of the system. That second part, finding the Lagrangian, is fairly easy, because we have to write down the kinetic energy minus u, that will be the Lagrangian. So now well, this is a question very specific to electromagnetic field, so we cannot stop but to introduce the Maxwell's equation of motion. So the Maxwell's equation of motion will be the del cross E is we know that this is also equal to del dot B. So del cross E is del dot B, and we see that del cross E is 0. So the first equation is del cross E is 0. So which means that of course E can be written as grad of phi, or we have a conservative system, right? That is how the cross product will be 0, or the curl is 0. Then also we see that del dot B is 0, the second equation, and from here we can 0. So from here we can conclude that B must be of the form del cross A, where A will be related to our answer, which is the velocity potential. So let us now take, for the electric field, we work only with the ordinary potential, right? So for the electric field E, of the force, for the electric field of the force, we take the ordinary potential. Right? And we take the potential V to be equal to E times phi r, the ordinary potential, right? And then for magnetic field, the magnetic field B of the force, we are going to choose, we will write the form of the velocity potential, and we will show that it is indeed the velocity potential. So we will claim something and we will prove our claim, right? So the magnetic part is we choose the velocity potential as Q of R is equal to minus E times R dot with A of R. Right? So what is A of R? A of R is related to the magnetic field, B is del cross A. Right? And I'm choosing my velocity potential to be Q of R. I'm choosing my Q of R to be, which is the generalized force, to be minus E times R dot AR. This is my generalized force. Okay, so which means, well, something is missing here. Hold on. I think the sign convention is a little confusing. This last sign has to be capital U and not capital Q, because that is a velocity potential. Okay, so we are back. Then let us now, what we are, so this is our claim that, look, this is our velocity potential. We will show that it is indeed the velocity potential, that is, it indeed satisfies the the Maxwell's equation. So what we have is, let us look at U. So U is now is R dot R, AR. Okay, we have divided by minus E, that's a constant, that's the charge of the electron. And let us now look at this quantity here. So this is going to be X dot, so R dot with AR. So this is X, well, this is X dot AX of R plus Y dot AY of R plus Z dot AZ of R, right? And we see that, let us call this AX to be partial U partial X dot and AY to be partial U partial Y dot. We are defining this, right? And AZ to be partial U partial Z dot, right? And now what we have is that partial U partial X or partial R, partial U partial R is going to be, or partial X bar is going to be, is going to be, of course, X dot AX. X dot AX is, hold on, what have we done here? Just a minute. We don't want to calculate partial U partial X bar. So here is our U, and here U is given. So now I am going to differentiate U with respect to the X component X, right? So partial U partial X is going to be X dot times partial A partial AX partial X plus Y dot times partial AY partial X plus Z dot times partial A Z partial X, right? And we see that now if we were to calculate what is this expression, d dt of partial U partial X dot minus partial U partial X. Remember, partial U partial X dot is this quantity is nothing but AX, right? That can be clearly found using this expression here, because X dot only appears in the first term here, right? So now we see that this expression is going to be d dt of AX minus X dot partial AX partial X minus Y dot partial AY partial X minus Z dot partial AZ partial X, right? And we see that I can rewrite this partial AX partial, dAX dt using the fact that using the chain rule, that this quantity is going to be partial AX partial X times X dot plus partial AX partial Y times Y dot plus partial AX partial Z times Z dot, right? It's only this quantity here, right? And we see that after clubbing this together and simplifying, so we have 1 2 3 4 5 6 terms. We simplify everything. We will have some cancellations. For example, this cancels with this, but the other cancellation will not happen. But we are going to be remaining that this is going to be equal to minus Y dot times partial AX partial AY partial X minus partial AX partial y and plus z dot of partial ax partial z minus partial az partial x. Right? So those are the four terms remaining, and we can write this four terms in the more vector form notation or the generalized vector form, and this is minus y dot times del cross a of z plus z dot of del cross a of y. What is this? Z means the z component of del cross a, and y means the subscript y means the y component of del cross a. So then similarly we can see that this del cross a is nothing but b. So this is minus y dot times bz minus z dot times by, right? And similarly we can find out what is this component for when you differentiate with respect to y and then you differentiate with respect to z, and eventually we will see that we are going to, so this is nothing but, this quantity is nothing but our qx, right? Qx, well, I should say what is qx, hold on. So I am calling this as q. So what is the relation between q and u? U is q divided by minus e. Minus e is a constant, right? So we have found the x component of q, which is qx, and we can see that this is nothing but minus of r cross with b. This is the x component minus r dot cross with b. And similarly we can find qy and qz, and we can, so the process is that qy is going to be minus r dot cross b, which is the y component, and similarly qz will come out to be minus r dot cross b, which is the z component. And now when we multiply all these three quantities, qx, qy, qz with minus e, multiply with minus e, and we see that we get the so-called the velocity potential, right? So we get that u comes out to be e times, well, let us multiply with plus e. So we get is as minus e times r dot times dot with ar. So that is my u. That is what we began to begin with, and that is what we have seen. Okay, so which means the final part of the problem is that the net potential v of r is going to be E times phi r. What is E times phi r? This is coming from the electric field part. Remember, from the electric field, the potential was very simple because it was a conservative. Electric field was had its curl equal to 0. So the electric field gave us a simple form of the potential, and minus E times r dot times dot product with ar, and this is our total potential. The potential due to electric field, the potential due to magnetic field, the total potential. And we can now write the Lagrangian. The Lagrangian is T minus V, and that is going to be half m r dot with r dot product. So that is my kinetic energy minus V, which is E times phi of r, plus E times r dot with A of r. So that is my Lagrangian. And we can see that the Lagrangian can help us from, well, this question now remains, we are going to wrap up our discussion, but we are going to wrap up our discussion with a question to the audience. This question is, we have so far developed a theoretical construct, the Lagrangian. What is the relation between its physical counterpart Hamiltonian. We can surely associate Hamiltonian with the energy of the system. Now the question remains, what is the relation between the Lagrangian and the Hamiltonian, which we are going to see in our next module. So that is the food for thought today. Okay, so the Lagrangian will help us to find the Hamiltonian, and this is a very common quantity of pursuit in quantum mechanics. So we will see how we construct the Hamiltonian, and people who are interested to work in quantum mechanics will surely find this discussion very useful. Thank you so far for listening. Thank you.